Okay, ladies and gentlemen, let's continue with the previous lecture. We are still busy on the work of the differential equation for linear momentum. This chapter is chapter 4 in the textbook of White. We are doing differential relations for fluid flow, and the first part of the chapter was about the acceleration field of a fluid. The second one was on mass conservation. We've completed that. We're now busy with the linear momentum differential equation, which is going to be followed by the angular momentum one and the energy one. Then a part on boundary conditions, the stream function, and then vorticity and irrotationality, and then frictionless irrotational flow, and some examples on incompressible viscous flow. So that is the scope of the work that we're going to do. Let's just revise quickly in terms of the most important work that we've done with the previous lecture. We've started by also looking at a control volume, and in this case we are interested in forces because Newton's law is all about forces. So we said that the sum of the forces is equal to partial ddt of the integral, the control volume integral of the velocity vector rho dv, the volume, plus the sum of the product of the mass flow rate multiplied by the velocities going out minus what is coming in, and that would be the sum of the forces. We've looked at this small control volume and said we can make the assumption that we can write that term as that. In the previous lecture we've numbered that as equation 2, that one is equation 3, and then we've said let's look at all three the directions, in the x direction, the y direction, and in the z direction, looking at what is coming in and what is going out, and using the differential approach across a small delta x, where we know what the gradient is to determine what is going out, and then we can do that in all three directions. And if we do it in all three directions, it looks like this. There you go. So there it is in all three directions in different colors, so that you can identify it a little bit better in terms of what is going on. So that is the inlet momentum flux, and that is what is going out. And again we can see that that term and that term will cancel out. The same in the y directions and in the z directions, and the result is that we can end up with this equation. Not directly, the equation is going to look more complex like that, but we can use the continuity equation which we've derived previously, which gives us three terms which is equal to 0, and we can make some of those terms equal to 0, and the result is that we end up with this simpler equation looking like that, from which we can say that the sum of the forces is equal to this equation. However, what we did is we've only concentrated on, let's call it, the right-hand side of the equation. We didn't really look at the components involved on the left-hand side of the equation. Now, on the left-hand side, the sum of the forces, there are two types of forces. The first one, body forces, and the second one, surface forces. So let's first look at the body forces. Now, the body forces that we as mechanical engineers are interested in is usually gravity, but there are other types of external body forces like magnetism or electrical potential, so they can also be used. And for us as mechanical engineers, usually we would say that the gravity force is equal to rho multiplied by g dx dy dz, and in this chapter the tradition has been developed where usually the coordinate system is with z in an upward direction. So z is usually in an upward direction, so that g is in this direction. Okay. So g is then equal to minus g in the z direction. So that is usually how we're going to write the body force. The other types of forces which are important are the surface forces. The surface forces. And that's now a little bit more complicated. The surface forces are directly proportional to the surface tensions multiplied by the areas. And this is now where things become more complicated. And what we use is this type of nomenclature by saying that sigma ij is equal to, the first term is minus p plus tau xx, the second one is tau yx, and the third one tau zx. That is the first line, and the second line is tau xy. This one is equal to minus p plus tau yy, that one tau zy, this one tau xz, tau az, and then minus p plus tau zz. And this relates to a control volume where we use the following notation. That is the x direction, that is the y direction, and that is the z direction. Where sigma ij is the stress in the j direction. Okay. So the second term, the j, gives us the direction. Okay. The second one is the direction, and the first one, the face, normal to the y-axis. Okay, now if we look at this face, then we will see that this face is normal to the x-axis. Okay, so therefore, this is always going to be an x. If we look at the three different directions of the stresses. So, like that. First one is an x, okay, to give us the face. And the second one gives us the direction. So this direction is in the x direction, this one is in the z direction, and that one is in the y direction. This face is normal to which axis? The z-axis. Okay. So the stresses would look like this. Sigma z, the first one gives us the face, and the second one gives us the direction. That is in the x direction, that one is in the z direction, and that one is in the y direction. Okay. This face is normal to, which axis? The y one. So the first one is going to be y's, and the second one gives us the direction. That one is in the x direction, that one is in the y direction, and that one is in the z direction. So 9 of the stresses on 3 of the surfaces. So that's only half of them. There's obviously the other half on the other sides. Okay, that I'm not going to try to show to you. This is just going to be too messy. Okay. So what we're starting to have is vectors and tensors. What is the difference? So the velocities, the velocity components, will have three components, and they are called vectors. Now the stresses, doesn't matter in which form, all the deformations, they need 9 variables to describe them with. So they've got 9 components, and they are called tensors. Okay, now what is interesting, and I don't know if you've picked it up with the derivation of the momentum equation and with this equation, but what you will see is that the forces are not being influenced by the absolute values, but by the differences. And this is a very important thing, a very important concept. It's the differences that is important. Doesn't matter what the stresses are on the control volume. If you measure it in pascals, kilopascals, megapascals, or whatever, the absolute values are not important. It's the differences over the control volume which is important. Okay. So it is not the stresses. But the gradients. The gradients or the differences. That cause a net force. So the net forces are being caused by the differences and not so much by the absolute values. Okay, so if we now look at the sum of the forces, if we look at the sum of the forces, and we look typically only in the x direction, then we're going to have a stress on that surface there in the x direction. I'm only referring to the x direction now. To the x direction. There's going to be one there, there's one going to be there at the back, there's one going to be on that surface there, and we are going to have on that surface sigma xx dy dz. And here we're going to have sigma xx plus d sigma xx dx partial multiplied by dx multiplied by dy dz. Okay, and that term is going to cancel. And that is the reason why we say it is the gradients which are important and not the absolute values. Okay. So in the x direction, there's now going to be 1, 2, 3, 4, 5, 6 terms that we need to take into consideration with the sum of the forces, and we have to take the gravity also into consideration if there is a gravity or a body force in the x direction. So writing it out is a little bit messy, but it can be done. Use a large paper and It's preferably if you've got a small handwriting, it helps. But it can be written out, and the result of that is the linear momentum equation that looks like that. So that is now how it looks like in the x direction that we previously derived. Okay. These terms are now the result of putting it all together, doing a little bit of mathematical manipulation, and that is then the linear momentum equation in the x direction. You can see rho gx, okay, so it's the gravity or the body force, plus the three surface forces, T sigma xx dx plus d sigma d tau yx dy plus d tau zx dz is equal to rho multiplied by du dt plus u multiplied by partial du dx plus v multiplied by partial du dy plus w multiplied by partial du dz. That's the equation in the x direction. Similar equation in the y direction and in the z direction. I hope you can see it. It doesn't seem as if it is so clear, but I've used different colors there for the different directions, trying to make it a little bit more clear. Okay. But that's not really going to help us a lot, that equation, unfortunately. Because again, if I tell you that in a flow field the stress is somewhere so many newtons per square meter, so what? You as a mechanical engineer, it is not something that really means something. We as mechanical engineers prefer things like velocities and pressures. That is what we can work with. That is what we want to measure, and that is what we are interested in. So we have to change those stresses to other stuff. Okay, how do we do that? Okay, and before we do that, we can also write the linear momentum equation in a different format, in a shorthand format, and that format looks like this: rho g, the vector, minus the pressure force plus the grad of tau ij is equal to rho dv dt. Rho g is the gravity force per unit volume. Okay, rho g, the gravity force per unit volume. The grad of P is the pressure force per unit volume. Okay. The divergence of the stresses is equal to the viscous forces per unit volume. And the last term is just the density multiplied by the acceleration. Okay. Sometimes if we look at that equation, we do not really see immediately that that is nothing less than the acceleration term. So it is rho multiplied by dv dt is equal to density multiplied by acceleration. So that's the meaning of all the terms. And before we get rid of all the stresses, there are some assumptions that can be made. The first type of assumption is called the Euler equation. Okay. The Euler equation is when we say that all the flow is frictionless. Frictionless flow. Okay. If the flow is frictionless, it means that all the tau ij terms is equal to 0. So if we look at this linear momentum equation of us, then we can take out those 9 terms. That 3 terms, those 3 terms, and those 3 terms gives us the Euler equation. Now the Euler equation is an important equation because it feeds into another equation. Can you remember which one? The Bernoulli equation. So if we make the assumptions that all the stresses are equal to 0, so it's frictionless flow, and we say it is incompressible and 2D, then from there it follows to the Bernoulli equation. So with more assumptions. The Bernoulli equation is the equation with about more assumptions than any other equation. Okay, the Bernoulli equation. Okay. Now how do we get rid of all those stresses? Well, fortunately other people did some work, and we are not going to do this derivation here, but you will see these same terms when you look at the studying of strength of materials. Okay, in terms of that generalization to 3D viscous flow, it can be shown that tau xx is equal to 2 times the viscosity multiplied by partial du dx. Where does that come from? It comes from the fact that previously in white you've said that the viscous stresses is equal to the viscosity multiplied by du dy. Do you remember that? Okay. So there's a linear relationship between the stress and the gradient on a control volume. Okay. Now that would typically be for the tau xx term. For the tau yy term, it is equal to 2 times the viscosity multiplied by dv dy. And I'm sure you can figure out what is the z1. So I'm not going to write down the z1 now. But the other terms, tau xy, which is equal to tau yx, is equal to the viscosity multiplied by partial du dy plus partial dv dx. So that is typically how that one looks like. I'm not going to write down all of them, just to give you a typical idea of how they look like. And then tau yz, for example, is equal to tau zy is equal to the viscosity multiplied by partial dv dz plus partial dv dy. And in the textbook of White, it referred to reference 5, which is also work of this specific author, in which I think he gives all the details or the derivation of these terms. Okay. So this gives us the relationship between the stresses and the velocity gradients, which we now have to put into that equation. Okay. So if we go and put it into that equation, that is what we're going to get. Rho multiplied by gx is equal to, which are equal to that terms, is now going to, if we do the calculations, it's going to give us those terms there. Okay. Now take note, this is what makes the differential equations non-linear. This is the non-linear part. If we've got, as I've mentioned, if we say that we've got frictionless flow, then all that would be equal to 0, and then we've got the Euler equation. Okay, so that is the linear momentum equation in terms of how we get those terms into gradients. And the result is, if we do now a little bit of manipulation, then we get these very, very important equations. Okay. So rho multiplied by gx is equal to minus the p dx. That is the body force. The surface force plus the viscosity multiplied by those terms is equal to rho multiplied by du dt. Okay. Three different directions. These equations are called the Navier-Stokes equations. Because in the derivation from here to there, we've made the assumption that the viscosities are constant and also that the density is constant. Okay. These are the equations that you're going to solve in CFD. Okay. They are not always valid because there are fluids which are non-linear. Okay. And if they are non-linear, the relationship between the stresses and the viscosity, for example, your blood, for example, is such a type of a fluid, then these equations would not be valid. Okay, so you have to go back then and put that correct relationship in, and then you will use that equations. But mostly in mechanical engineering, those are the equations that we solve, and those are called the Navier-Stokes equations. Okay. Now the procedure that we followed now for the derivation of the linear momentum equation, that same procedure can be followed for the derivation of angular momentum. Okay. We are not going to do it in detail. The equations are given in your textbook. Don't take note of them. Then the next one is the differential equations for energy. The differential equations of energy. Again, we go through a similar procedure, and this is the result of the energy equation. That is how it looks like in a compact form. Okay. Rho d hat dt plus p multiplied by that is equal to that, where hat u is equal to cv dt, and that phi can be written like that. So that's the energy equation, a differential energy equation. And when you want to solve a CFD problem where there's heat transfer or temperature gradients, then you need to also solve this equation together with all the other equations. Okay, paragraph 4.6 is on boundary conditions. And we are not going to go through it in detail. It doesn't mean that you shouldn't go through it in detail. You should work through it. You know that differential equations, if you've got a differential equation and you want to solve it, you need boundary conditions. Okay. The boundary condition determines the outcome of the equation. And also in CFD, you cannot solve the differential equations if there are not boundary conditions. Okay. So go and work through it and make sure you understand it. Okay, ladies and gentlemen, that is the lecture for today. Any questions? If not, then I'll see you again on Monday. Thank you very much.